Hello and welcome to lesson number 24, Cartesian circles. To start off this lesson, let's begin by defining what a circle is. For our purposes, a circle is going to be all the collection of points such that those points are equidistant and having a distance r from a center which I'm going to call AB. So then in this case we can see any point x, y on this circle would have to have a distance r from the center point a, b. From this video here, we know how to find the distance between any two given points. From the formula derived in that video, we can see the distance r is going to be equal to the square root of the x-coordinate distance, which is going to be x minus a squared, plus the distance of the y-coordinate squared, which is going to be y minus b squared. Now, we can square both sides, and there's nothing wrong with doing so since everything is positive and there's no like square roots of negative numbers or anything like that in here. Due to this, we can write that r squared is going to be equal to this thing on the right squared, which is going to be x minus a squared plus y minus b squared. At this point, we're actually done for our first form for the equation of a circle. We can rearrange this actually because that's normally how we write it. We normally write that x minus a squared plus y minus b squared equals r squared is the equation of a circle. Any points x, y that are on the circle will satisfy this equation, and any points which are not on the circle will not satisfy this equation. So then we can write that this is the equation of a circle which is centered at the point a, b and having a radius r. An example of such a circle would be something like x plus 3 squared, so let's say x plus 3 squared, and then plus y minus 2 squared equals 16. This is an equation that defines a circle. To find out which circle it defines, we need to reconvert this back into this form that we have here. Doing so, we can see that x plus 3 would be equal to x minus negative 3 whole thing squared. And then here we have the y minus 2, which we can leave as is, y minus 2 squared. And this 16 is actually 4 squared, so I can write equal to 4 squared. Now we can see that this equation that we have here is of the form x minus a squared plus y minus b squared equals r squared. And from this form, we know that given this equation of x minus a squared plus y minus b squared equaling r squared, we know that it describes a circle with a center of a, b and a radius of r. According to that, from this formula, the center of this circle that's being described by this equation here is negative 3, 2. As for its radius, it is equal to 4. So this circle equation here is representing a circle which is centered at negative 3, 2 and having a radius of 4. This, however, is not the only way that we could represent a circle in an equation. There are other ways. This way has x minus a squared and y minus b squared unsimplified. The way that we're going to be discussing now is actually derived by simplifying this thing and taking everything to one side. This is one of those equations where you have something on the left equal to 0 on the right. So to get this second form of a circle, what we're going to do is start with the first form and simplify it. To do so, let's start with x minus a squared plus y minus b squared equal to r squared. At this point, we know exactly what each of these symbols means. The a and b are the coordinates of the center of the circle and r is the radius of the circle. Now then, simplifying this out, x minus a squared gives us x squared minus 2ax plus a squared. As for y minus b squared gives us a y squared, a minus 2by and a plus b squared, which is equal to r squared. What we're going to do now is take this x squared term and y squared term to the front, and next we're going to put the negative 2ax and the negative 2by. We're going to take this a squared and b squared to the end, and we're also going to take this r squared to the other side, and we're going to try to group all three of these constants together. Doing so, what we get is that this equation simplifies down to x squared plus y squared minus 2ax minus 2by plus a squared plus b squared minus r squared equal to 0. At this point, we actually do a substitution. We substitute negative a for a value called g, and we substitute negative b for a value called f. So let's just do that. Let's say let g be equal to negative a, f be equal to negative b. So we're doing a substitution of f and g. And here we can see, since g is equal to negative a, g squared is equal to a squared. So we can simplify this a squared into a g squared. As for this, f is equal to negative b, therefore f squared is going to be equal to b squared, so we can substitute this b squared for an f squared. Doing all of these substitutions, we can get that this equation turns into x squared plus y squared, and then this minus a turns into a g, so then we have plus 2gx. This minus b turns into a positive f, so we have plus 2fy, and then this a squared turns into a g squared, so we have plus g squared. This b squared turns into an f squared, so we have plus f squared, and this minus r squared remains as is, and it's all equal to 0. There's one more substitution we do to finish this off. Since g squared, f squared and r squared are all constants, g squared plus f squared minus r squared is also some kind of constant. Because of this, we write all of this as being a single constant, which we usually call c. So then, writing the rest of the equation down, we had that the equation of the circle that we derive from this is equal to x squared plus y squared plus 2gx plus 2fy plus the constant c equal to 0. Now then, in this format, there is still a way to interpret these symbols. We can interpret g, we can interpret f, and we can interpret c. In order to do so, however, we're going to be needing our original formula. From our original formula, we know the interpretation of these symbols. The a and the b are the coordinates of the center, as in a comma b is the coordinates of the center, and r is the radius of the circle. Bringing that over to this equation here, since we know that g is equal to negative a, we also know that a is equal to negative g, and we also know that from this equation, f is equal to negative b, therefore b is equal to negative f. So if a is equal to negative g and b is equal to negative f, then the coordinates a comma b are the same as the coordinates negative g comma negative f. If the coordinates a comma b correspond to the center of the circle, then in this format, the center of the circle, which I'm going to write as center, is equal to the coordinates of negative g comma negative f. Therefore, with this format, negative g comma negative f are the coordinates of the center of the circle. How about the radius? Well, to get the radius, we can use this equation here. We know that g squared plus f squared minus r squared is equal to the constant c. Rearranging this equation, we can see that g squared plus f squared minus c would be equal to r squared. All I've done here is written this down as c equals to g squared plus f squared minus r squared, and then rearranged the r squared and the c. Now then, since r is a positive value and we would expect for a normal circle this thing to also be a positive value, we can say that r must be equal to the square root of g squared plus f squared minus c. So then, according to this, the radius of the circle, which I'm going to write down as radius, is equal to the square root of g squared plus f squared minus c. Now, for a normal circle which has a positive radius, this thing inside the square root would be positive. For a circle that has 0 radius, as in r equals 0, this should all be 0. So the whole sum here should be 0. If the whole sum is 0, then g squared plus f squared must be equal to the constant c. However, with this form, it is also possible for c to be a value that is bigger than g squared plus f squared, in which case this thing inside of the square root would actually be negative. When we have an equation like this, we know that this circle does not actually exist, as in there are no points within the real numbers that satisfy this circle. So there's an added condition here that c must be less than or equal to g squared plus f squared. And in the absolute extreme case, where c is equal to g squared plus f squared, the radius of the circle is equal to 0. Now, we can use this to find equations of circles that are actually bogus. If for any equation of a circle, c is any value that is greater than g squared plus f squared, we know that that circle does not actually exist within the real numbers. In fact, we can slowly change c and bring c closer to g squared plus f squared, and we can see what happens to the equation of the circle as we do so. I'll put an animation of that right now, and as you can see, when c approaches the value of g squared plus f squared, the circle gets really small, and as c passes the value of g squared plus f squared, the circle disappears. That is because the radius of the circle is actually a complex number, at which point there are no real solutions x, y for that circle. So therefore the circle simply does not exist within the real numbers. Let's take a look at this equation of a circle right here. This circle is actually bogus. It does not exist within real numbers, and what we're going to do is show that it actually does not exist within the real numbers. To start off, let's compare it with the normal general formula for a circle, which is going to be x squared plus y squared plus 2gx plus 2fy plus c equals 0. Comparing terms, the x squared and y squared are alright. As for the 8x is compared with the 2gx, meaning that g must be equal to 4. Comparing the negative 2y with the 2fy, we can see that f must be equal to negative 1. Comparing these two terms, we can see that c must be equal to 70. Now then, from our equation from earlier, we know that the center of this kind of circle must be equal to negative g, negative f. According to this, the central coordinates of this circle here are negative 4, negative 1 or positive 1. Therefore, the central coordinates of this circle are negative 4, 1. As for its radius, we know that the circle has a positive radius and does exist if g squared plus f squared is anything bigger than c. Now then, taking a look at what we have here, g is equal to 4 and f is equal to negative 1. As for c is equal to 70. Comparing them, g squared plus f squared minus c is equal to 4 squared, which is 16, plus negative 1 squared, which is going to be equal to 1, minus c, which is going to be 70, which is 17 minus 70. This is a negative value, which already raises the concern that this circle actually doesn't exist within the real numbers. It is equal to negative 53. If we actually try to do the calculation and we try to calculate the radius r based on the formula r is equal to g squared plus f squared minus c, we would get that the radius r is equal to the square root of negative 53 or 53i. Therefore, this circle is actually bogus. It does not have any real solutions. There are no points within the real coordinates that match on this circle. With this, we have shown that for this form of a circle, there are certain values of c for which the circle simply doesn't exist. Let's now move on to deriving some common relationships with circles. The first relationship we're going to derive is the equation of a circle which has endpoints x1, y1 and x2, y2 to its diameter, as in the points x1, y1 and x2, y2 are the endpoints of the diameter of some circle. Given that information, we're going to try to find the equation of the original circle, as in this circle here. In order to do this, we're going to be using the geometrical fact that if you have a circle like this, the lines from one end of its diameter to some point on the circle and the other end of the diameter to the same point on the circle are going to be perpendicular to each other. In fact, this is true for all points on the circle. So if I draw, for example, this point here, this is also perpendicular. In fact, for all points not on the circle, it's not perpendicular. So the perpendicularness of these two lines is unique, and we can use that to find the equation of the circle. Through this, what we're going to do is define this point, which is an arbitrary point on the circle, as x, y. And now that we've done that, we can find the gradients of this line and this line. To do that, I'm going to label the gradient of this line as m1 and the gradient of this line as m2 and write them down. The gradient m1 is the difference in y coordinates divided by the difference in x coordinates, which I'm going to write as y minus y1 divided by x minus x1. As for the second gradient m2 is equal to the second difference of y coordinates, which I'm going to write as y minus y2, so y minus y2 divided by the second difference of x coordinates, which is going to be x minus x2. Now then, from this video on the top right here, we know that if two lines are perpendicular, then their gradients multiply to negative 1. Therefore, m1 multiplied by m2 must be equal to negative 1. We can now substitute the values of m1 and m2 in, which are y minus y1 divided by x minus x1 and y minus y2 divided by x minus x2. This must be equal to negative 1. Now then, what we're going to do is to take this x minus x1 and x minus x2 to the right side here and then rearrange this equation. Doing so, we get y minus y1 times y minus y2 being equal to negative x minus x1 times x minus x2. Usually what we do is to take this thing to the other side and write that the equation of this circle is x minus x1 times x minus x2 plus y minus y1 times y minus y2 equal to 0. Therefore, given 2 points x1, y1 and x2, y2, if we know that these 2 points are the endpoints of a diameter of some circle, then we can say that the equation of that said circle is this right here. So for example, if we have the points, let's say 2, 3 and let's say 5, 7, we know that the equation of the circle with this line as a diameter is x minus 2 multiplied by x minus 5 plus y minus 3 times y minus 7 equal to 0. Let's now move on to our next topic, which is going to be about how a line and a circle intersect. It turns out there are 3 specific ways in which a line and a circle can intersect. They have been written down here as case 1, case 2 and case 3. Case 1 is the case where the line goes right through the circle, intersecting it at 2 total points. The next case, case 2, is what we call tangency, and it happens when the line just touches the circle, connecting with it at only a single point. The third and final case is when the line and the circle do not intersect at all. You can see here, this circle and this line never touch. Let's discuss how we can figure out when a given line and a given circle are in case 1, case 2 or case 3. To do so, let's consider a generic circle and a generic line. Here I have generic circle S being given by x squared plus y squared plus 2gx plus 2fy plus c equal to 0. As for the line, I have a generic line U given by lx plus my plus n equal to 0. Now in this case, from what we know about circles, we know that the central coordinates of this point O are negative g, negative f. We also know that the radius of the circle R is equal to the square root of g squared plus f squared minus c. Now, what we can see from this particular example is that the line is outside the circle. We can also see that this length here, from here to here, is the radius of the circle, and the perpendicular distance from the center of the circle all the way out to the line is greater than the radius r. As it turns out, this perpendicular distance between the line and the circle is going to be the property that we are using in order to see whether we have case 1, case 2 or case 3. Going back to case 1, case 2 and case 3, we can see in case 1, this perpendicular distance here is less than the radius of the circle. In case number 2, we can see that the perpendicular distance is exactly equal to the radius of the circle, meaning that this point, which is the perpendicular distance r away from the center of the circle, is on the circle. As for the third case, we can see when the line is outside the circle, the distance from the center up to the line itself is going to be greater than the radius of the circle. Therefore, what we need to do is to try and find the distance between the center of the circle and the line, and using that, check whether it's greater than, less than or equal to the radius of the circle in order to see whether we are in case 1, case 2 or case 3. The perpendicular distance from a point to a line is given by this formula here, which I'm going to write as d equal to the absolute value of ax0 plus by0 plus c divided by the square root of a squared plus b squared, where the point we're interested in is x0, y0, and a, b and c are constants of the line, which is of the form ax plus by plus c equals 0. Replacing the symbols that we have, we can see that the distance d is equal to the absolute value of L times negative g plus m times negative f plus the constant n divided by the square root of L squared plus m squared. This is a direct substitution into what we had earlier. Now then, simplifying this a little bit, we can see that the perpendicular distance d between the center of the circle and the line is going to be equal to the absolute value of n minus lg minus mf divided by the square root of L squared plus m squared. So all you have to do is compute this value and see whether it is bigger, smaller or equal to the radius r. According to this, if d is less than r, we are in case 1 where the circle is intersected twice by the line. If d is equal to r, we are in case 2 where we have a tangent. And if d is greater than r, we are in case 3 where the line does not intersect the circle at all. So if ever you want to figure out whether a line is intersecting a circle twice, once or not at all you have to do is compute this value here and see if it's bigger, smaller or equal to the radius of the circle. Our next topic of discussion is actually related to case number 2 of the above, that is the tangency case. It is to do with the tangent to a circle. Specifically, given a point through which a tangent passes, which I have marked as x0, y0, and the equation of the circle to which the line is tangent, how do we find the equation of the tangent line? So basically here in this setup, I've drawn out the circle and the line tangent. I've drawn out the point tangent to be x0, y0, and I've drawn out the circle S to be given by x squared plus y squared plus 2gx plus 2fy plus c equal to 0. I've also drawn out the point that is the center of the circle, which is negative g comma negative f, and the radius of the circle r. The geometrical fact that we're going to be using in order to find this equation of this tangent line here is going to be the fact that given a point of tangency x0, y0, the radius that is correspondent to that point of tangency is perpendicular to the tangent itself. You can see I've drawn that by the fact that this angle here is 90 degrees. So we're going to be using this fact in order to find the equation of this tangent line here. To start off, let's suppose that the gradient of this radius is m1 and that the gradient of the tangent is m2. We know that if two lines are perpendicular to each other, then the product of their gradients is equal to negative 1. Therefore, m1, m2 must be equal to negative 1. We also know m1. We know m1 because we know two of the points on the line R. Here we can see we know the point x0, y0, and we also know the point negative g comma negative f. Using this, we can write that m1 is equal to the y coordinate difference, which is y0 minus negative f, so I'm going to write that as y0 plus f, divided by the x coordinate difference, which is x0 minus negative g, which I'm going to write as x0 plus g. Using these two equations, we can find the gradient of the tangent line m2. So I'm going to go down here and write that m2 is equal to, according to this equation, m2 is equal to negative 1 divided by m1, which is equal to negative 1 over m1, which is going to be x0 plus g divided by y0 plus f. Writing that down, m2 is equal to x0 plus g divided by y0 plus f. So therefore m2 is equal to negative x0 plus g divided by y0 plus f. Now let's try and find the equation of this tangent line. To do this, let's consider a random point on this line as x comma y. This is some arbitrary point that's on the tangent line. So now, given this arbitrary point on the tangent line and the other point that we know on the tangent line, we can find the equation of the tangent line. How we're going to do that is to consider the gradient given this point, this arbitrary point on the line, and the known point x0, y0, and equate that to m2. So then, doing so, the gradient given these 2 points xy and x0, y0 is going to be y minus y0 divided by x minus x0. And we know that this has to be equal to the value of m2. Therefore, y minus y0 divided by x minus x0 is equal to negative x0 plus g divided by y0 plus f. Rearranging, we can see that y minus y0 is equal to negative x0 plus g divided by y0 plus f times x minus x0. After a little bit more rearranging, we can get that y minus y0 multiplied by y0 plus f is equal to negative x minus x0 times x0 plus g. Taking everything to one side, we can see that x minus x0 times x0 plus g plus y minus y0 times y0 plus f must be equal to 0. Now we could leave it at that, but we can actually simplify this further. In order to simplify this further, what I'm going to do first is to take this negative x0 times this component here and this negative y0 times this component here to the other side of the equation. So basically I'm going to leave this x times x0 and x times g on this side, as well as the y times y0 and y times f. Doing so, what we get is x times x0 plus y times y0 plus g times x plus f times y on the left side, and taking everything else to the right side, here we have an x times x0 times x0, which is x0 squared. We have an x0 times g, which I'm going to write over here as x0g. We have a y0 times a y0, which is going to be y0 squared, and we have y0 times f, which is going to be y0f. So this is what we have. What we're going to do now is go back up and consider this point on the circle and use it to find another equation that we can use to make that equation for the tangent line simpler. So what we're going to do is consider this point here and notice that this point is on the circle and the circle S is given by this equation here. Therefore, the coordinates x0 and y0 must satisfy this equation here. Therefore, we can substitute for x, x0, we can substitute for y, y0, and it will still be a true equation. So, x0 squared plus y0 squared plus 2gx0 plus 2fy0 plus c must be equal to 0. We know this to be true. We can copy this down and use this to substitute into our equation that we have so far. So writing this down, we can copy this down here and I'll leave it right about there. And we can use this equation to simplify this equation for the tangent that we have here. We can simplify it by the fact that this x0 squared and y0 squared are contained in this equation, as are one of the x0g's and y0f's that we need to simplify. What we don't have is the other x0g and y0f. Here we can see there's two x0g's and two y0f's. But up here, we only have one x0g and one y0f. We can make this equation on the left be equal to this thing on the right by simply subtracting a c, subtracting one of the gx0's and subtracting one of the fy0's. Doing so, we get that x0 squared plus y0 squared plus gx0 plus fy0 is equal to negative gx0 minus fy0 minus c. Using this, we can now substitute all of this stuff that we have on the right for this expression that we have here. Doing so, if we go down here, doing so we get on the left the normal x times x0 plus y times y0 plus gx plus fy, but on the right side what we have to substitute is this stuff here, which is negative gx0 minus fy0 minus c. Now what we're going to do is take all of this to one side and group terms and simplify. Grouping terms, taking everything to one side and simplifying, we get x times x0 plus y times y0. Taking this negative gx0 and this gx to one side, we can see that what we get is g times x plus x0, and taking this fy and this negative fy0 together, we get plus f times y plus y0, and then taking this c to this side, we get a plus c. And then this is all equal to 0. This is the standard way that we normally write the equation of the tangent line to a circle at a point x0, y0 on the circle. You can see that this thing almost resembles the equation of the circle itself. The equation of the circle itself is x squared plus y squared plus 2gx plus 2fy plus c equal to 0. You can see here, instead of one of the x's, we have an x0. Instead of one of the y's, we have a y0. Here as well, instead of two x's, we have one of the x's and one x0. Here, instead of two y's, we have one y and one y0, and the c remains as it is. This is the equation of the circle, and this right here is the equation of tangent line that passes through the circle at a point x0, y0 that is on the circle. As it turns out, naming a point on the circle and finding the tangent on that point is not the only way for us to define tangents to a circle. Instead of finding a point on the circle, we could also define tangents based on a point outside the circle, like I've done here. Here you can see I've marked a point external to the circle as x1, y1, and given such a point, there are exactly two tangents to the circle that will pass through this point here. You can see this first tangent touches the circle at this point here, continues like this, and touches this point here, x1, y1. As for this other tangent, it touches the circle at this point right here, continues like this, and also goes through this point external to the circle here. So, we can define these two tangents based on this external point here and the equation of the circle. As it turns out, however, if we want to try and find these two equations of the two tangents, it becomes slightly complex. Rather, if we want to try and find these two equations of these two tangents, what we have to do first is to find a different line's equation, and that line is this line through these 2 points here. This line is called the chord of contact. The chord of contact of a circle is the line that passes through the 2 points at which the two tangents drawn from a point external to the circle touch the circle. So here this point and this point here are the 2 points that define this line, which is known as the chord of contact. It turns out, if we can find the equation of this line and apply it to the circle, we can more easily find the equations of these two tangent lines than trying to do the whole thing directly. So let's attempt to try and find the equation of this chord of contact here. In order to do that, what I'm going to do first is to define these 2 points where the circle has been touched by these 2 tangents. We're going to define this point up here as x2, y2, and this point down here as x3, y3. Now at this point, let's assume we know these 2 points x2, y2 and x3, y3. Given that, we can find the equations of these 2 tangents, which I'm going to label as t1 and t2. We can find them because, as we found above, given a point x0, y0 on the circle, the tangent line that goes through that point is going to be given by this equation here. Using that and substituting, we can write that this tangent t1 is given by x times the x coordinate of the point, which is in this case x2. So we can write x times x2 plus y times the given y coordinate, which is y2, plus g times x plus x2 plus f times y plus y2 plus c equal to 0. Similarly, we can find the equation of the tangent t2 based on this coordinate here and write that the equation t2 is given by x times x3 plus y times y3 plus g times x plus x3 plus f times y plus y3 plus c equal to 0. These 2 equations are the equations of the tangents t1 and t2. Now what we're going to do is observe the fact that t1 and t2 both must pass through this point here, which is x1, y1. Given that both of these tangents t1 and t2 pass through the points x1, y1, substituting x equals x1 and y equals y1 to both of these should yield an answer of 0, as in both of these have the point x1, y1 on them. So therefore, we could write, substituting x1 and y1 into this equation, that x1 times x2, as in substituting this x for x1, plus y1 times y2, so substituting y1 into that, y1 times y2, plus g times x1 plus x2 plus f times y1 plus y2 plus c must be equal to 0. I'm going to call this equation number 1. Similarly, since the tangent t2 also passes through x1, y1, we can also write, substituting x1, y1 into this equation here, that x1 times x3 plus y1 times y3 plus g times x1 plus x3 plus f times y1 plus y3 plus c must also be equal to 0. I'm going to call this equation number 2. Now at this point, I'm going to do a little leap of faith and I'm going to consider the line x times x1 plus y times y1 plus g times x plus x1 plus f times y plus y1 plus c equal to 0. Alright, we're going to consider this line here. Considering this line, I want you to think about whether this line passes through the points x2, y2 and x3, y3. So, given this line like this, which I'm going to call capital L, considering capital L, if capital L passes through the point x2, y2, then substituting x equals x2 and y equals y2 should give us a proper solution, as in substituting those 2 values into here, it should be equal to 0. And then similarly, if this same line passes through the point x3, y3, then substituting x equals x3 and y equals y3 into this equation should also give us 0. So, if we consider doing that, substituting x equals x2 and y equals y2 into this thing, we can see we get x2 times x1 plus y2 times y1 plus g times x2 plus x1 plus f times y2 plus y1 plus c equal to 0. But we can see from equation number 1 that x1, x2, y1, y2 plus g times x1 plus x2 plus f times y1 plus y2 plus c is equal to 0. So based on that, from 1 we could say that L passes through the point x2, y2. Similarly, if we consider the point x3, y3, right? Considering this point, if x3, y3 is a point on the line L, then substituting x equals x3 and y equals y3 into this equation should give us 0. But from statement number 2 we can see when we do exactly that for each of these, we do in fact get an equals 0, meaning that this point x3 y3 is also on the line L. So we can say from statement number 2 we can see that L does in fact pass through the point x3, y3. Now then, if this line L passes through the points x2, y2 and x3, y3, and as we know, there is only one line that passes through these 2 points. If the line L passes through these 2 points, then the line L must be the line that we're looking for, the line corresponding to the chord of contact. Therefore, this line here is the line that we'll be looking for, line L. So we can see the line for the chord of contact is given by xx1 plus yy1 plus g times x plus x1 plus f times y plus y1 plus c equal to 0. Now you might notice actually here that this thing looks suspiciously similar to the equation for the tangent line that passes through a certain point on the circle. And you're right, it is in fact 100% true. The way that you can interpret this is by considering bringing this point extremely close to the circle like this. If you do that, as you bring this point extremely close to the circle, then the 2 points at which the 2 tangents to this circle are going to be touching the circle are going to be extremely close to each other. In fact, in the limit that this point becomes arbitrarily close to the circle's surface, these 2 points are going to be extremely close to each other and also close to this third point that we're considering here. When that happens, the line that is drawn between those 2 tangent lines, as in the chord of contact, and this tangent line itself that is drawn from the surface of the circle like this, are going to be identical. Due to that, the line for the tangent at a certain point x0, y0 on the circle and the line for the chord of contact from an external point to the circle do look extremely similar. It is because when that point external to the circle gets really close to the circle itself, the line corresponding to the chord of contact becomes arbitrarily close to the line corresponding to the tangent of a point that is on the surface of the circle. At this point you may be wondering, alright, we found the line L, how does that help us in finding the equations of the tangents T1 and T2? It actually helps us a lot and almost gets us to the final answer, because now that we know the line L, we can find x2, y2 and x3, y3. How can we do that? We can do that by rearranging L in order to get x equals or y equals. So as in, we take all the x terms to one side, we take everything else to the other side, and we get either x equals some function of y or y equals some function of x. Once we get this, if we substitute that equation into the circle S, we will be getting a quadratic. The quadratic solutions that we will get from that equation will be either the 2 x coordinates x2 and x3 for these 2 contact points, or the 2 y coordinates y2 and y3 for these 2 contact points here. Once we have that, we can then resubstitute those points back into L to get the corresponding x coordinate. As in, if we have x2, we can substitute into L to get y2, or if we have y2, we can substitute into L to get x2. Given that we can get x2, y2. Similarly, if we have x3, we can substitute into L to get y3, or if we have y3, we can substitute into L to get x3. At that point, we will have x2, y2 and x3, y3. Once we have x2, y2 and x3, y3, we can then substitute those into T1 and T2's equations that we have here in order to finally get full equations of the 2 tangents T1 and T2 from this external point x1, y1 to the circle. Now, we cannot actually do this in a single step and get T1 equals this line and T2 equals this line. We could do it, but the radicals and all of that will make the algebra very messy and ugly. So instead, general process that we will do and ask to find the 2 tangents would be this thing right here. We would first find the chord of contact L. We would then take the chord of contact equation, substitute it into this circle here to find the 2 coordinates, the x coordinates x2, y and x3, or y2 and y3, and given that find the other coordinates x2 and y2 correspondingly to find x2, y2 and x3, y3, at which point we would then substitute them into these two equations to finally find the two tangents t1 and t2. So I'm actually going to do an example question of this to show you how it's done, and then we will continue to our next component of this lesson. So let's try and use our knowledge on this simple question here. We have an external point 8, 3 which is external to this circle here, given by x squared plus y squared minus 2x minus 4y minus 20 equals 0. Our task is to find the equation of the two tangents that are going like this and this. So to do that, let's first draw out the two tangents that we want to find. The two tangents are the two tangents that pass through the point 8, 3 that go like this and this. So these are the two tangents that we want to find. As we discussed, in order to find these two tangents, the first thing we're going to do is to consider the chord of contact, which goes something like this. We just derived the equation for this thing, which we're going to write down as L given by what? Going up here, we know that if we have an external point x1, y1, then the chord of contact of the two tangents is going to be given by x times x1 plus y times y1 plus g times x plus x1 plus f times y plus y1 plus c equals 0. Applying that to this situation, we have x times x1, which is 8, so we can write like 8x plus y times y1, which is 3, so we can write 3y plus g times x plus x1. Now here in this case, considering this thing, this is going to be 2gx. If 2gx is negative 2x, then g must be equal to negative 1. So we can actually replace this plus sign with a minus sign and say minus 1 times x plus x0, so x plus 8. And then next we have f times x plus x0. In this case, we have 2fy being equal to negative 4y. Therefore, f must be equal to negative 2. So we can write negative 2 times y plus y0, which in this case is going to be y plus 3, plus the constant, which is negative 20, so minus 20 equals 0. Therefore, the line L is given by this expression here. Simplifying this down, we can see that we have 8x here and minus x here, which we can write down as L being given by 7x, and then this 3y, this minus 2y can be simplified down to just a single y, so plus y. And then in terms of constants, this minus 8 and this minus 3 times 2 can be written as minus 8 minus 6 or minus 14. And then we have another minus 20. Combining that all into one constant, we have minus 34 equal to 0. We can rearrange this to get y in terms of x as we discussed above, and in this case we get that y is equal to, in this case, this negative 34 to the other side will become positive 34, and this 7x to the other side will become negative 7x. So y is equal to 34 minus 7x. The next step, as we discussed, would be to substitute this thing into the circle's equation. So doing so, we can see x squared remains as it is, so we get x squared, and then this plus y squared needs to be replaced with this, so we get plus 34 minus 7x whole thing squared, and then from this bit we get minus 2x as normal, and then minus 4y, which is going to be 34 minus 7x minus 20 equals 0. Now what we need to do is simplify this down, find x in terms of the constants that we have here, in which case we are going to get a quadratic, which means there are two values of x. The two values of x that we are going to get are the x coordinates of this coordinate here and this point here. So let's try and solve this quadratic and find x, and then once we find x, we can also find the corresponding y values for those two coordinates, write them down and use them to find the equation of the two tangents. Simplifying this thing, we can see we have x squared. Expanding this thing, we have plus 34 squared, and then minus 2 times 34 times 7x, and then minus 7x squared is going to be plus 49x squared, and then minus 2x here. This thing is going to give us minus 4 times 34. This bit and this bit are going to give us plus 28x, and finally we have minus 20, all equals 0. Rounding up x squared terms, we can see we have 1x squared term here and 49x squared here. That means a total of 50x squared. Next, considering x terms, here we have minus 2 times 34 times 7x. Here we have minus 2x, and here we have a plus 28x. We can take these two together and get a plus 26x. As for this thing, we need to multiply this thing through. 2 times 34 is 68 times 7. So we'll do 68 times 7 here. 7 times 8 is going to give us 56. As for 7 times 6, that's going to give us 42, so 420. So we get 476. Subtracting 476 here, because here we can see there's a minus here. Subtracting 476x from this thing, we get negative 450x. So therefore we have negative 450x in this equation. I'm going to get rid of this rough work here, and we're going to go next on to the constant terms. My apologies, this is actually plus 34 squared. We also have on this side a minus 4 times 34 and a minus 20. So here we can actually take this plus 34 squared and then this minus 4 times 34 together and write this as being 34 times 34 minus 4, as in 34 times 30. From this 3 times this 30 will give us 900, and this 4 times this thing will give us 120. So we have a total of 1020. This minus 20 from that will give us a total of 1000 as the constant term. So our constant term here is 1000. So we have plus 1000 equal to 0. Now at this point we can notice that this quadratic equation can have all of its coefficients divided by 50, because here this has a factor of 50, this has a factor of 50, and this also has a factor of 50. Dividing out by 50 we get x squared minus 9x plus 1000 divided by 50, which is going to be 20, equal to 0. Now all we have to do is simplify this quadratic equation in order to get x equals. We will get two values. One of the values corresponds to one of these points here, and the other value corresponds to the other point, at which point we can then find the corresponding y coordinates and finally find the equations of the two tangents. So then, simplifying this thing, we know the quadratic formula. If you don't know that, click this video in the top right here. It is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So substituting that, x equals negative b, which is negative 9. So we have negative 9 plus or minus the square root of b squared, which is going to be negative 9 squared, minus 4 times a, which is going to be 1, times c, which is going to be 20, all divided by 2 times a, or 2 times 1. Now then, simplifying this, we can see that this negative 9 gives us positive 9, so plus 9, and then this bit gives us plus or minus the square root of 9 squared, which is going to be 81, so we have square root of 81, minus 4 times 20, which is going to be minus 80, all divided by 2. Here we can see that 81 minus 80 is going to be 1, and the square root of 1 is going to be 1. So what we really have here is x equals 9 plus or minus 1 divided by 2. Therefore, there are two values of x. The first value we're going to take is the plus case. The plus case, x is equal to 9 plus 1 divided by 2, so 10 divided by 2, which is 5. Or the second case where we have minus, so we have 9 minus 1, which is 8, divided by 2, which is 4. So we have x equals 4. Now then, in each of these cases we have corresponding y. We can find the corresponding y's from this expression here. Here we have y equals 34 minus 7x. Copying that down here what we need to do is y equals 34 minus 7x, which is going to be y equals 34 minus 7 times 5, which is going to be 35. So 34 minus 35, y equals negative 1. So the corresponding coordinate from this is going to be 5, negative 1. This is going to be the coordinate number 1 for our first tangent. For the second tangent, again we are going to apply y equals 34 minus 7x. In this case, x is equal to 4. So we have y equals 34 minus 7 times 4, which is going to be 28. So we have 34 minus 28, which is going to give us 6. So in this case, y is equal to 6. So therefore, the second pair of coordinates that we get is 4, 6. Now what we need to do is to take these two coordinates as being the two coordinates at which the tangents are touching, at which point we can use the earlier formula that we discovered in order to find the two tangents. I'm not going to go back to recall that. If you want, we are going to have to skip backward to try and find that formula. I remember the formula, and the formula is going to give us that the tangents are corresponding to these two equations here. The first tangent is going to be 5x minus y plus, actually it's going to be minus, since g is negative 1, so minus 1 times x plus the x coordinate, so it's going to be x plus 5, and then the f is going to be negative 2, so we have minus 2 times y plus the initial y coordinate, which is actually negative 1, so I'm going to write as minus 1, and then plus the constant, which is negative 20, equals 0. This right here is the equation for the first tangent. Again, the first tangent and second tangent are arbitrary. I'm just choosing this one as being the first tangent. For the second one, we need to use these coordinates. Doing so, we get 4x and then plus 6y minus 1 times x plus the x coordinate, which is going to be x plus so x plus 4, and then minus 2 times y plus the y coordinate is going to be y plus 6, plus the constant which is minus 20 equals 0. Now we can simplify these. I'm not going to do that step because it's unnecessary, but these two equations are the equations for the two tangents to this circle that are coming from the external point 8, 3. Since doing all of this in one step is impractical, the method that you're going to have to use is this method here, where we first find the chord of contact, and then using the chord of contact, find an equation of y in terms of x or x in terms of y, substitute that into the circle to get a quadratic equation, simplify that quadratic equation in order to find the two x coordinates or two y coordinates corresponding to the two places where the tangents touch the circle, and finally, using our equation for a point on the circle, find the equations of the two tangents like this. The next and final thing we need to talk about regarding tangents is going to be the length of a tangent. Specifically, given some external point, what is the length of the tangent from that external point up to the point where the tangent touches the circle. So here I have marked the external point as P, given by x1, y1. I've marked the point of contact as Q, and I've also drawn the center of the circle O as negative g, negative f, which will be useful in finding the length PQ. Here the circle is given by the standard equation x squared plus y squared plus 2gx plus 2fy plus c equals 0. Here we can see the length OQ is in fact the radius r. I'm going to write down the formula that we derived for that, saying that r squared is equal to g squared plus f squared minus c. We're going to be using this in now solving to find the length PQ. Now, let's make some observations. This angle here is 90 degrees. We know that from the radius and tangent being perpendicular to each other. Also consider the length OP. The length OP is opposite to this right angle here. So inside of the triangle OPQ, this side is the hypotenuse. So you can see this is the hypotenuse and these are two other sides, PQ and OQ. Considering this right angle triangle, we could apply the Pythagorean theorem. Applying that, we can see that the hypotenuse squared or OP squared must be equal to the sum of the other two sides squared, which is going to be PQ squared plus OQ squared. I'm going to write plus OQ squared. We have this identity. Now then, let's try and figure out what each of these values are. Considering OP squared, OP is the length between the points O and P. We know the coordinates of P and we know the coordinates of O. Therefore, we can find the length OP. The length OP is going to be the square root of the x difference squared plus the y difference squared. Therefore, if we take OP squared, it would be the square root of the x difference squared plus y difference squared, whole thing squared, which will get rid of the square root, leaving us with just the x difference squared plus the y difference squared. So therefore, substituting that in, we can say that OP squared would be equal to the square root of the x difference squared, which is going to be the coordinate x1 minus negative g squared. So we can write that as x1 plus g squared plus the y difference, which is going to be y1 minus negative f, which I'm going to write as y1 plus f. So y1 plus f squared, whole thing squared. On the other side, if we consider PQ and OQ, PQ is the value we're going to find. For that reason, we're going to leave PQ as it is. So I'll just leave it as is and write PQ squared plus OQ squared. OQ squared is going to be r squared, since OQ is equal to r, and we know that r squared is equal to g squared plus f squared minus c. For now, I'm just going to leave this as r squared, and we're going to simplify it in the next line. So then, what we want to find is PQ. So let's isolate PQ by taking this r squared to the other side. Doing so, we get that PQ squared is equal to, simplifying this thing, this square root and this squared will cancel, leaving us with just x1 plus g squared plus y1 plus f squared, and then minus this r squared on the other side, so minus r squared. Now then, let's expand and simplify each of these terms. Here we have that PQ squared is equal to, so expanding this thing we get x1 squared plus 2gx1 plus g squared, and then expanding this thing we get plus y1 squared plus 2fy1 plus f squared, and then expanding this r squared using this formula that we know, r squared is equal to g squared plus f squared minus c. Therefore, minus r squared is equal to minus g squared minus f squared plus c. Substituting that in, we have minus g squared minus f squared plus c. Now then, at this point we can see over here we have a plus g squared, over here we have a minus g squared which can be cancelled, and then similarly we have a plus f squared here and a minus f squared here which can be cancelled like this. And then if we consider what we're left with, pq squared is equal to x1 squared plus, and I'm actually going to take this y1 squared to the front to keep the pattern, so we're going to have x1 squared plus y1 squared. Next I'm going to write this 2gx1, so we have plus 2gx1 and plus 2fy1 plus 2fy1 and then plus c. So this is the value of pq squared. Now pq is a length. Here pq is the length of the tangent from the point P to the point Q. Therefore pq is a positive value. If pq is a positive value, when we take the square root of both sides, we don't have to put a plus or minus or anything since we know it's the positive value. So we can just write that pq is equal to the positive square root of everything on the right, which is x1 squared plus y1 squared plus 2gx1 plus 2fy1 plus c, and that is our answer. Here we can see a very striking similarity to the equation of the circle itself. The equation of the circle itself is x squared plus y squared plus 2gx plus 2fy plus c equals 0. And over here, the length of the tangent is x1 squared plus y1 squared plus 2gx1 plus 2fy1 plus c, and that is that. We kind of have like the formula of the circle substituted with the x1 and y1 inside, and that whole thing square rooted. Now it should be noted that this value could be negative, and as it turns out, the way that you get this value to be negative is if you take this point P to be a point that is inside of the circle. Because if you think about it, on the surface of the circle, that value would be equal to 0, as in if P is a point on the circle, this thing substituted would be equal to 0. And as it turns out, if we have a point outside, then this value here is a positive value. Therefore, when we are inside the circle, the value substituted into this thing here is actually negative. So here, if x1 and y1, x1 comma y1 is a point that is inside of the circle, then we get a negative value inside of the square root, in which case taking the square root of that, we get a complex number. So just know that if inside of the square root when you're substituting x1 and y1 you somehow get a negative number, that means that the point x1, y1 is inside of the circle. Otherwise, if the point x1, y1 is outside of the circle, you will get a positive value which is going to be equal to the length of the tangent starting from the external point up to the point where the tangent touches the circle. Our next topic of discussion is going to be the different ways in which two circles can intersect. Now for this discussion, we are only going to be talking about the different ways in which two circles that have different radii are going to intersect. The reason for this is that if we have two circles of the same radii intersecting, other than the set of intersections that I have listed here, there is actually one more intersection that could potentially happen. That intersection is the intersection where the two circles perfectly overlap with each other. So let's say this is one circle, the other circle perfectly overlaps with it like this. We're not going to be discussing this intersection because it's like a very special case, and we're instead going to be generally thinking of two circles that have different radii and how they can intersect with each other. So for this thing, we're going to be considering two circles of different radii. Let's suppose that the radius of the smaller circle is r1 and the radius of the larger circle is r2. Let's also suppose that we label the center of the circle that has a smaller radius r1 as c1 and the center of the circle that has a larger radius as c2. So here you can see in this first example, this c1 point is representing the circle center of the circle that has a radius r1, and the point c2 is representing the center of the circle that has a radius r2. Now then, based on that definition, let's carry on and start talking about this set of intersections. The first intersection, intersection number 1, is the intersection where one circle is completely inside of the other circle. We can see that there is a line that we could draw in between these two circles, and the first circle, the smaller circles with radius r1, is completely inside of the circle of radius r2. In order to figure out the condition for this thing to happen, let's draw the line starting from c2 that goes through c1 and all the way out to the surface of the second circle. In this case, if we consider the length from here to here, this length is r2. The reason for that is that this line here goes from the center c2 all the way up to the edge of the circle with center c2. Therefore, this is the definition of the radius of the circle c2, as in it's r2. Next, let's consider this length here. This length is R1 since it is the distance from the center C1 up to the edge of the circle C1. So this length here is R1. Let's suppose that we call this length here between the two centers of the circles as C1, C2, since the point here is C1 and this point is C2, and C1, C2 is representing the distance between C1 and C2. Now we can see that between the two circles here there is an extra little bit of distance that I'm going to call delta. Now if we consider writing the distance from this center C2 up to the outer surface of the circle with center C2, we can call it R2. We can also see that this length is equal to the length components C1, C2, and this length component R1, and this length component which we call delta. So therefore this total length is also equal to the distances C1, C2 plus R1 plus the extra length which we are calling delta. Now, given this equation, if we rearrange it to get C1, C2 on one side, we can see that C1, C2, the distance between the 2 points of the center of the two circles, is equal to R2 minus R1 minus delta, where R2 is the radius of the larger circle, R1 is the radius of the smaller circle, and delta is the little extra distance that we noted is there between the end of the first circle and the second circle's center and the second circle's edge. The second circle's edge. So then, if this is some positive distance and we are subtracting it, this means that R2 minus R1 is something bigger than the distance C1, C2. So given that, we could write this as having that C1, C2 is some distance which is less than R2 minus R1, where R2 is the bigger radius of the bigger circle and R1 is the radius of the smaller circle. So here we are essentially removing delta and turning this equal sign into an inequality. Now, since we assume that R2 is the bigger circle's radius and R1 is the small circle's radius, this is some positive value and the C1, C2 is of course some positive length. However, that was our assumption. We do not know whether the person who's doing this calculation would consider R2 to be the bigger radius and R1 to be the smaller radius. Therefore, to prevent this kind of ambiguity, let's add an absolute value sign across these two. That means we are considering that the bigger one is R2 and smaller one is R1 is no longer valid. It could be that the R1 radius is the bigger circle's radius and R2 the smaller circle's radius. To account for that, we are now putting an absolute value sign and just saying that the difference between the two radii is something bigger than the length between the two centers of the circles. So then, given that condition that we now don't know which one's the bigger radius, R1 could be the bigger radius or R2 could be the bigger radius, to account for that, adding this absolute value sign, we can say that now the condition for one circle to be completely inside the other circle is that C1, C2, the distance between their two centers, is some value which is less than the absolute difference of their two radii. So then that is the definition of the first intersection. For one circle to be completely inside the other circle, the condition is that the distance between their centers must be less than the absolute difference between their two radii. Now, moving on from that, let's consider the second intersection. This second intersection actually has a special name. It's called touching internally. As in, this first circle is completely inside the second circle, but it's touching the first circle internally at this point right here. So then, given this condition, how do we find a condition that we can use to write for this specific intersection? In order to do that, what I'm going to do is draw the line from the center C2 up to the point where the circles with centers C1 and C2 are intersecting. So basically I'm going to draw this line right here. Drawing this line, we can see, considering this radius right here, this radius is the radius R2 since it is a distance from the center of the second circle up to the surface of that circle. And now considering this distance is R1 since this distance here is the distance from the center of the first circle up to the surface of that circle. Now, unlike the first intersection, there is no additional delta distance in this entire length. Due to that, we can write that R2 is equal to this distance, which is the distance between the two centers, which I'm going to write as C1, C2, plus the distance R1. Therefore, rearranging this, we can see that the condition for this kind of intersection to occur is that C1, C2 is equal to R2 minus R1. Now once again, we are the people who assume that R2 is greater than R1. However, for some person who's randomly trying to use this formula, they might rearrange these two variables as r1 being the bigger circle's radius and r2 being the smaller circle's radius. To account for that, let's add an absolute value across this thing like this. Now we have that the distance between the centers of the two circles must be equal to the absolute difference of the two radii. So therefore, we can say that this is the condition for two circles to intersect internally, as in one circle is inside the other circle, but the two touch each other at a single point like this. Moving on to our third intersection case. The third intersection case is when one circle is partially inside the other circle, but the two circles intersect at 2 points like this. So here we can see there's one intersection here and another intersection here. In order to figure out the condition for this, what we're going to do is draw this line starting from the center of the second circle, going through the center of the first circle, out until it touches the edge of this first circle like this. Now then, considering the lengths involved, this length here is the distance from the center of the second circle up to the surface of the second circle, so it is r2. Now considering the distance from this point here up to this point here, this distance here is r1, since it's the distance from the center of the first circle up to the edge of the first circle. Now then, consider this little extra distance that we have here. I'm going to label this distance as a delta. Using this, we can see that if we consider instead of this distance r2, the distance for total from the center of the second circle up to this edge of the first circle here, this distance could be written as r2 plus this extra distance delta, which I'm going to write as r2 plus delta. However, we could have also written this distance as being equal to the distance between these 2 points c1, c2 plus the extra distance from c1 up to the end point here, which is r1. Therefore, this distance is also equal to c1, c2 plus r1. Now then, if we have this, we can rearrange this and get us that c1, c2 is equal to r2 minus r1 plus delta. Now, we can see if delta is some positive value and we have plus delta here, then this thing altogether is equal to c1, c2. Therefore, this component r2 minus r1 is some value that is smaller than the total sum c1, c2. So if we convert this equal sign into an inequality by getting rid of the delta, we could write that c1, c2 is some distance that is bigger than the distance r2 minus r1, since this is some positive value. Now there's actually another condition, but in order to write this condition, we're going to wait a little bit. We're going to go down and consider the next conditions and come back and rectify this condition here. There's actually another thing that this needs to be less than some other length, but in order to discuss that, we're going to consider the next intersection first. But for now, let's consider that r2 in our definition is the bigger radius. However, for a random person using this formula, they have no obligation to use r2 as the bigger radius. Therefore, to accommodate that, let's additionally put an absolute value sign in between these two, because they might choose r1 as the bigger radius. So therefore, in order to accommodate that, we say that the distance between the centers c1, c2 is bigger than the absolute difference between r2 and r1. Now then, in order to consider the second condition that we need to have here, let's go to our next intersection. The next intersection is where one circle is completely outside the other circle, but is touching at a single point like this. At this point, in order to consider the condition that we need, let's draw the line that is between the two circle centers like this. This length here is the length r2, since it is the distance from the center of the second circle up to the surface of that circle. Similarly, this distance right here is r1, since the distance from the center of the first circle up to the surface of that circle. Now we can see if we consider the center c1 and c2, the distance c1, c2 is equal to this distance r2 plus this distance r1. So therefore, c1, c2 is equal to r1 plus r2. Now in this case, we can see that there is no portion of this second circle that is inside of the first circle. And we can also see that as we break this second circle out of the first circle, like this, as in make the distance between c1, c2 bigger and bigger, eventually we are going to reach this point here. At this point, c1, c2 is equal to r1 plus r2. If we brought these two centers a little bit closer together, as in we brought c1 slightly closer to c2, then we can see that this distance c1, c2 would be slightly less than r1 plus r2. And additionally, there would be some portion of circle 1 that is inside of circle 2. And we can see that that would be belonging to intersection number 3. So therefore, there is an upper bound to C1, C2 in intersection number 3. It cannot be anything equal to or greater than R1 plus R2, because then we would no longer have part of one circle being inside of the other. Therefore, actually there's another condition that we have to add here. We have to add that the distance C1, C2 is a little bit less than R1 plus R2. In order to realize this condition being necessary, we need to move on to the next intersection. So now we have the full condition for intersection number 3. It is that the distance between the two centers C1, C2 should be less than R1 plus R2, but greater than the difference of the two radii R1 minus R2's absolute value. So that's intersection number 3 completed, and also intersection number 4 completed. Moving on to intersection number 5, if we consider intersection number 5, we can see that if we draw a line between C1 and C2 like this distance is R2, this distance is R1, and we can see there's an additional distance delta that we have to consider in order to consider C1, C2. So then if we write C1, C2's equation, C1, C2 is the radius R1 plus the radius R2 plus the additional distance which we are calling delta. So plus delta. Now, converting this equal sign into an inequality, we can see that R1 plus R2 must be some value smaller than C1, C2, since we need to add an additional positive value delta to R1 plus R2. Therefore, converting this into inequality, we can see that C1, C2 must be some value that is greater than R1 plus R2. And that concludes the set of simple intersections that we have to discuss. As it turns out, there's actually one more intersection that we need to talk about, but for now, these are the 5 simple intersections of two circles. There's another complex one that we're going to move on to next, and that intersection is something called the orthogonal intersection. Orthogonal intersection is a special case of intersection number 3, where one circle is halfway inside the other circle and the two circles intersect at 2 points, where the special condition is that if we consider one of the intersection points and draw the line from the center of one circle up to that point and the center of the other circle up to that point, the two lines drawn would be perpendicular to each other, as in they have a 90-degree angle between them, which is why this intersection type is called orthogonal intersection. Now then, given this information, let's try and figure out the condition that we can use in order to see whether two circles intersect orthogonally. In order to do this, I have defined the first circle S1 as being given by this equation, where the two center points is negative g1 comma negative f1, so that the circle gives this equation and the constant is c1. And the second circle S2 is given by the center negative g2 comma negative f2 and the constant c2. Now then, given this condition, let's try and figure out what we can use in order to find whether these two circles intersect orthogonally. Initially, the first observation that you will probably see is that this length here is R1 and this length here is R2, as in the center of the first circle up to the end of the circle is the radius of the first circle, as in R1, and the center of the second circle up to that corresponding edge is the radius R2. Now, we can actually use this and the fact that this is 90 degrees and this line here in order to find a condition that we could use in order to see whether two circles intersect orthogonally. And that idea stems from the Pythagorean theorem. Here we can see that this triangle that we've just created has a 90-degree angle on one side, meaning that the opposite side, which is this thing, is the hypotenuse. It turns out, since we know the center coordinates of the two circles, we can find this length here. And since we know all the constants involved, we can find R1 and R2. So then, R1 squared plus R2 squared must be equal to this distance squared if the two circles intersect orthogonally. This condition is what we're going to use in order to find whether two circles intersect orthogonally. Writing this down, we have that R1 squared plus R2 squared is equal to the difference of the x coordinates and difference of y coordinates squared of these two center points. Now then, writing this down, let's say that the x coordinate difference will be taken as negative g1 minus negative g2 squared. So we have g2 minus g1 squared plus negative f1 minus negative f2, which is going to be f2 minus f1 squared. Now, we know formulae for the radius r1 and radius r2 based on the other constants of the circle. I'm going to write that down up here and say that r squared is equal to g squared plus f squared minus c, where these constants here are all the standard constants that we have. Now then, given that, we can write that r1 squared is equal to g1 squared plus f1 squared minus c1, and r2 squared can be written as g2 squared, I'm going to put a plus here, plus f2 squared minus c2. Now then, expanding the thing on the right. On the right we have g2 squared minus 2g1 g2, and then this g1 squared, negative g1 whole thing squared is going to give us positive g1 squared. Expanding this thing we get plus f2 squared minus 2 f1 f2, and then minus f1 squared, which is going to give us plus f1 squared. Now then, cancelling out like terms. On the left we have g1 squared, on the right we have g1 squared. On the left we have f1 squared, on the right we have f1 squared. On the left we have g2 squared, on the right we have g2 squared. And on the left we have f2 squared, on the right we also have f2 squared. Cancelling all of this out, we can see what we're left with on the left is c1 minus c2, minus c1 minus c2. And on the right side what we have left is negative 2 g1 g2 and negative 2 f1 f2. So minus 2 f1 f2. Removing the negative sign, we can see that what we are left with is 2 g1 g2 plus 2 f1 f2 being equal to c1 plus c2. Now this is sufficient condition enough, and we've simplified it enough that people have decided that this is a good condition for us to check. So that's going to be the condition that we're going to check. If two circles are such that 2 times g1 times g2 plus 2 times f1 plus f2 is equal to c1 plus c2, where all of those constants are what they normally are in the equations of circles, given that kind of condition being satisfied, we can say that the two circles S1 and S2 intersect orthogonally. Now this is slightly different from the rest of the intersections, and we are actually required to remember this equation and use it in some certain equations. The next and final topic that we need to discuss within this lesson is going to be adding a line to a circle. The basic premise of this is the equation S plus lambda u equals 0. Here lambda is a constant. As for S and u, S equals 0 is representing a circle. So we can say S equals 0 is a circle. And similarly, u equals 0 is representing a line. So u equals 0 is a line. The basic idea here is that S is all the contents x squared plus y squared plus 2gx plus 2fy plus c, and u is all the contents ax plus by plus d. Now normally it would be ax plus by plus c, but since c is already used inside of the circle equation, I'm going to use d instead. So basically, S equals 0 is representing a circle x squared plus y squared plus 2gx plus 2fy plus c equals 0, and similarly u equals 0 is representing a line ax plus by plus d equals 0. Now here I normally would put c, but since c is already used, I'm using d instead. So given this, what we're considering is taking a portion of line, as in we're multiplying the line by a constant, as in we're getting a certain amount of line, and then we're applying that line onto a circle. So basically we're taking the circle, adding a part of line onto it, and we're saying what is that whole thing equal to 0 representing. So to work this out, let's just write out all of this. We know what S is all of this stuff here. We know what u is all of this stuff here. We'll just write that times lambda and see what we get. So S plus lambda u equals 0. This is representing S bit, which is x squared plus y squared plus 2gx plus 2fy plus c, plus lambda times the u bit, which is going to be ax plus by plus d equals 0. Here, of course, again I'm reminding you, d is used because c is already used in the circle's equation. Now then, let's try and figure out what this gives us. Here we can see we have an x squared term here, a y squared term, an x term, a y term, and a constant term. Within this part, we have lambda times ax, which is an x term, lambda times by, which is a y term, and lambda times d, which is a constant term. If we add all of the stuff on the left side together, we can see that what we have is an x squared, a y squared, a 2gx, and a lambda ax, which would be combined into a single x term as plus 2g plus lambda a times x, as in we're taking the x out and writing x outside here, and the whole coefficient of the x term is going to be all of this stuff here. Similarly, considering the 2fy and the lambda times by, we can write that as a common term as 2f plus lambda b times y. So that's the common y term. And then as for the constant terms, here we have a plus c, and here we have a plus lambda times d. We can write that as a common constant term as plus c plus lambda d equals 0. Now, we can see a pattern here. Once again, we have an x squared term, a y squared term, an x term, a y term, and a constant term. If we do some symbol rearranging, let's suppose that we keep this x squared as it is, this y squared as it is, but then we replace this term with 2 times g prime x, where 2g prime is equal to 2g plus lambda a. And similarly, if we take this 2f plus lambda b and replace it with a 2f prime and then do 2f prime y, and then similarly if we take this c plus lambda d, replace c plus lambda d with c prime equals 0, we can see that s plus lambda u equals 0 is representing x squared plus y squared plus 2g prime x plus 2f prime y plus c prime equals 0, where g prime, f prime and c prime are some new constants. This is the form of a circle. Therefore, s plus lambda u equals 0 is also representing a circle. S plus lambda u is another circle. If we try and think about the properties of this circle, we will see some interesting things. Now, in our syllabus, we think only about the case where the circle s equals 0 and the line u equals 0 intersect each other. But I'll actually link down in the description to a certain Desmos file where you can play around with the s's values and u's values and find the value of s plus lambda u equals 0 when s and u don't intersect as well. So for now, we're only going to consider the situation when s and u, as in s equals 0 and u equals 0, intersect. And given that condition, we're going to try and figure out what the circle s plus lambda u equals 0 is representing. So let's go. So here I've drawn out the line u equals 0 and the circle s equals 0. And here, as I said, we're going to only consider the case where these lines u equals 0 and s equals 0 circle are intersecting each other. Here we can see there are two intersection points. However, what I'm going to talk to you about also impacts the one intersection point case, as in the tangent case. But for now, we're only going to be discussing the two intersection point case. So let's suppose this intersection point here is x1, y1. And similarly, let's suppose that this intersection point here is x2, y2. We can see that the point x1, y1 is on u equals 0 and is also on s equals 0. Therefore, if we take the equation u equals 0, as in this equation here, instead of x if we substitute x1, instead of y if we substitute y1, ax1 plus by1 plus d will be 0. Similarly, substituting x equals x1 and y equals 1, y1 into this, we will also get 0. Similarly for x2, y2, since x2, y2 is on u equals 0 and s equals 0 both, substituting x equals x2 and y equals y2 into this and this will both give us 0. Now then, if we consider what s plus lambda u would give us, for the point x1, y1, s would be equal to 0. This bit here is equal to 0. And also for the point x1, y1, u would also be equal to 0. Similarly, for the point x2, y2, which is down here, for this point x2, y2, s would be equal to 0. As in, if we substitute x equals x2 and y equals y2 into s, it would be 0. And if we substitute the same thing into u, this would also be 0. So here we have, in both cases, 0 plus lambda times 0. Considering 0 times lambda plus 0, we know that that must be equal to 0 no matter what lambda is. So then, given that, what does this mean? Well, if x equals x1 and y equals y1 are satisfactory for s and satisfactory for u, such that s plus lambda u, the whole thing, is equal to 0, then x1, y1 are satisfactory for the equation s plus lambda u equals 0. Therefore, substituting x equals x1 and y equals y1 into this equation here will also give us 0, as in it will satisfy this equation. Therefore, this point x1, y1 is on the circle being represented by this equation here. Similarly, for the point x2, y2, since x2, y2 satisfies S and it also satisfies U, it satisfies the entire equation S plus lambda U. Therefore, x equals x2 and y equals y2 is a solution for the circle resultant from S plus lambda U. So, if x equals x1, y equals y1, as in x1, y1 and x2, y2 are both solutions for the circle S plus lambda U, that must mean that the circle S plus lambda U passes through both of these points. I'm now going to play you a simple animation where I'm changing lambda and showing you what happens when we have different values of lambda for S plus lambda U. As you can see, for every single value of lambda, the circle resultant, which is going to be the black circle here, is passing through the two intersection points of the original circle S equals 0 and the original line U equals 0. Therefore, S plus lambda U equals 0 is going to give us a bunch of circles that pass through the intersection points of S equals 0 and U equals 0. You will be required to use this information in some questions, perhaps not obviously, like it might not be obvious or they might not tell you to use this information. However, using this information on occasion will be quite useful. That is the end of this lesson. So we've learned about a lot of things about lines and circles. I recommend that you yourself take some past papers and see if you can figure out where to apply these principles in context, or simply ask an AI language model or your teachers or something to give you some questions related to this and exercise your ability in identifying and using the patterns that we've discussed in this video. So then that's the end of this lesson. I hope you've enjoyed. Thank you for watching and goodbye.